Okay, today we're going to be starting to look at differential equations, and we will be looking at specifically how to separate variables. So firstly, what is a differential equation? Well, a differential equation is something that you've already come across. So any equation that has excuse me, a derivative such that dy by dx, or even a second order derivative, d2y by d2 by x squared. Any equation that you can find its derivative of is a differential equation. So all the equations that you have been integrating are differential equations. So say we had dy by dx equals 3x squared. Y is going to be x cubed plus c. And this is what we call the general solution. Now, if we have some more information about the equation and the circumstances around that equation, we can find a particular solution. So say c equals 0, y equals x cubed, that would be the particular solution. And these are things that you have been solving and dealing with. Now, we can come across equations that are a bit more complicated. So, let's look at solving an equation like this. Dy by dx equals 6 to the power x plus 1 squared. We can use one of what we would call our differentiation methods. So, basically different forms of integration. So what we do here is basically we're integrating both sides. This might seem a bit of overkill writing it out like this, but this will become clear when we get into something a bit more tricky. And so these dx's cancel out, and so we'd end up with this side, the integral of dy, which just becomes y, and then this is going to solve. This becomes over 3 plus c, so y is 2x plus 1 cubed plus c. So this is the general solution. So in general, if we have some function f of y, so some function of y, dy by dx with respect to x is equivalent to integrating f of y with respect to y. What does that mean? Therefore, if we were to integrate the f by dy, f of y, dy by dx, it's equivalent to integrating f of y dy, because those bits would cancel out. Now, let's consider integrating something like solving a differential equation dy by dx equals xy when y is greater than 0. So how would we solve this differential equation? Well, the first thing to do is we need to separate the variables. We can't have the x and y on the same side. So we're going to divide through by y. So this will be 1 over y dy by dx equals x. And now we're going to integrate both sides. So 1 over y dy by dx equals the integral of x dx. Now this is going to cancel out. So we just get, so this then becomes the integral 1 over y dy, and this is the integral of x dx. Now we can integrate both sides of these. So we'll get the log of y plus, now we're going to call it a constant a, equals x squared over 2 plus, we'll call it b, which can be rewritten as, I'll write it over here, the log of y equals x squared over 2 plus our constant c. So we can just group the constants together and call it this. Now if we want to solve for actually y, we can take the exponential of both sides. So y is going to be the exponential of x over 2, x squared over 2 plus exponential of c, which we can add that together to be e x squared 2 plus c, and we can rewrite that as y equals d e to the x squared over 2, where d is e to the c, and that's just some arbitrary constant. Now, if we want to solve this for, this is our general form. So let's say, I'm going to do this down here, let's say that when y equals 2 when x equals 0. So we can put these in. So the log of 2 is equal to x squared over 0 squared over 2 plus c, and that just gives us c is equal to the log of 2, which we then will bring down, and so putting that into our y equals 2e x squared over 2. If you back that into this bit here. So by separating the variables, and we are rearranging differentiation, so the differential equation, so we get it into this form. Everything that's a function of y on this side, dy by dx, and everything that's a function of x on that side. And then we integrate both sides. And obviously these bits cancel out, so we have the integral of our function with respect to y integrated with respect to y, and our integral of our function of g of x with respect to x. So in the case where the derivative is where dy by dx is an expression of x only on one side and an expression of y times dy by dx on the other. So let's do some examples to see this at work. So we have a differential, differential equation dy by dx equals 1 plus x over 2y. It's given that y equals 3 when x equals 0. Solve the differential equation. So we have dy by dx equals 4x over 2y. So we want to take the function with respect to y onto this side. So we'll multiply both sides by 2y. And now, well, it's not 4x, it's 4. Dearie me. Sorry. That's just really badly written. That's meant to be 1 plus x. 1 plus x, 1 plus x. So now we can do our integral. 2y dy by dx equals the integral of 1 plus x dx. So that's going to give us the integral of 2y dy equals integral 1 plus x dx. Sorry, I'm overkill, but just want you to make sure that you understand that step here. And so then we're going to integrate that like we normally do. So it's going to be y squared equals x plus x squared over 2 plus some constant c. Now, we know y equals 3 when x equals 0, so 3 squared is going to be 0 plus 0 plus c, so c equals 9. So our equation is going to be y squared equals x plus x squared over 2 plus 9, or we can write that as x plus x squared over 2 plus 9 to the power of a half. Okay, let's do another one. Find the general solution of the differential equation x squared plus 1 y cubed plus x squared dy by dx equals 0. So let's bring this over to the other side. So it's minus x squared plus 1 y cubed. Now let's get rid of the x on this, the x squared on this side, and let's get rid of the y cubed on this side. So we'll end up with 1 over y cubed dy by dx, and we will have minus x squared plus 1 over x squared. Now, note this, take note of this. We've got a y here. So we need to assume y doesn't equal 0. So here we have the integral of y to the minus 3 dy equals the integral of, now we can rearrange, I'm going to just do this up here. We've got x squared plus 1 over x squared. This can be rewritten as x squared over x squared plus 1 over x squared, which is 1 plus x to the minus 2. So we're going to use this in here, but remember there's a minus here. So we've got minus x squared, x to the minus 2 minus 1 dx. So this gives us minus 1 over 2x squared equals 1 over x minus x plus c. Now, we said that x can't equal 0. But what happens if we look back to our original differential equation, if we look at this one here, x equals 0, dy by dx equals 0. So y equals 0 is a solution. So this is the general solution, or y can equal 0 as a separate solution to this equation. Let us do another one. It is given for 0 less than x, x between 0 and 300, dx by dt. Note the difference in variables. Now we're dealing with x is in t's, not y's and x's. Equals x to the x 300 minus x over 600 when x equals 50 and t equals 0. Find a particular solution for this differential equation. So we have dx by dt equals x times 300 minus x over 600. This time we want to bring the part with x's in it over to the left hand side. So we'll have 1 over x times 300 minus x dx by dt is equal to 1 over 600. Oops. Now we're going to integrate. And the dt's will cancel out here, so this will just be dx, and this is going to be the integral of 1 over 600 with respect to t. Now, we're going to play about with this expression here, and we're going to take out 300, and we're going to have 1 over x plus 300 minus x dx, because 1 over 600 dt. Now, when you get something like this, you're trying to rearrange the function so that it's in a form of something that you know you can integrate. So when you see 1 over x, there's two x's here, and you've got the inverse, and you're finding an integral, you're thinking this is probably going to be something logarithmic. And so you're trying to put it in a form that you can solve the integral to give you a log. And that's what we've now got. So now I'm going to carry on up here. 1 over 300 log of x minus the log of 300 minus x, and that equals 1 over 600 t plus c. Now, and I'll write this as, those can cancel out, and this will be rearranging it so with the rules of logarithms, x over 300 minus x equals half t plus c. Now, we know when x equals 50 is when t equals 0. So plugging these in, the log of 50 over 300 minus 50 equals 0 plus c. So c is going to be, working out that, but there's a log of 0.2. And I am running out of space. I'm going to carry on a new sheet. So we have, I'll write what we have. We have the log of x over 300 minus x equals a half of t plus log 0.2. Now we want to find this as a function for x. So we're going to take the exponential of both sides. So that's going to give us x over 300 minus x is equal to e the half t log of 0.2. And if we separate that out, we've got log of half t plus e to the log of a 0.2. Rearranging, we get x equals 0.2, because that's just going to, the e and the log will cancel, 0.2, and then we've got e to the half t, 300 minus x. We've brought this over to this side. And multiplying this out more, 1 plus, an extra step, sorry, we'll do an extra step because that's going to be a bit confusing. So multiply this bracket out and we're going to have x to the 60 e to the half t minus 0.2 e to the half tx, and now we're going to bring the things of x over here, so we'll have, I'll do it on this up here, x plus 0.2 e to the half t x equals 60 e to the half t. And on this one we can take the x out. This is a lot of work. This will give us 1 plus a half 0.2 e to the half t equals 60 e to the half t, and then x is going to be 60 e to the half t over 1 plus 0.2 e to the half t. That is a very long and fiddly bit of algebra at the end there, but we get there in the end. So I hope that makes sense.